Okay, so section 2.6, which is implications of quantum theory when we're talking about atoms and chemistry, and there's sort of three implications that I want to talk about. Spectroscopy, that we went over a little bit before, but also magnetism and periodic trends. So let's start with spectroscopy. Spectroscopy, like we were talking about before, is where either energy is absorbed from a photon or energy is emitted as a photon, and you get absorption and emission spectra from atoms and from molecules, characteristic to that atom or molecule. So this really shows you the orbital theory behind it, how when you're absorbing energy from a photon, so h nu, that's the Greek letter nu, not v, that's the energy of a photon. If you're using a wavelength or a frequency specific to the energy difference between the lowest occupied orbital and the highest occupied orbital and the lowest unoccupied orbital, the electron will jump up and absorb that specific wavelength, and then it will jump down and it will emit that specific wavelength. And we'll talk a lot more about this when we're talking about molecular orbitals, but when we're talking about spectroscopy before, we were talking about hydrogen atoms. You can calculate using the Rydberg formula the exact energies involved. You can't do that for multi-electron systems because the math doesn't work out to be anywhere near as nice as for hydrogen-like atoms, but you can determine experimentally what some of these values are just by looking at absorption and emission spectra for elements and for molecules. Another thing that can sort of be explained a bit better by orbital theory is magnetism. So there's two types of magnetism I want to talk about, both of which are fairly different to what most people think about with magnetism. Most people think about ferromagnetism, which is magnets that you stick onto your fridge, and has a more complicated basis in chemistry. Diamagnetism and paramagnetism are what I'll talk about, and these are where elements or molecules have unpaired or paired electron spins. So either all the electron spins are paired, and that's a diamagnetic molecule, or some of the electron spins aren't paired, and that's paramagnetic. And diamagnetic are usually either not affected or sometimes repelled by the magnetic field, depending on the substance. And paramagnetic are when you have unpaired electron spins, they're attracted by a magnetic field. A good example, the most popular example, is O2. Now, this is a molecular orbital diagram, and we'll talk about all of these a lot later, but you get the idea. Sort of the same as an atomic orbital diagram. You have orbitals filled with 2 electrons each, and you can see in oxygen you've got 2 unpaired electron spins in this pi star, which is an anti-bonding orbital up here, and that actually causes the oxygen molecule, the oxygen diatomic molecule, to be paramagnetic. So if you put liquid oxygen through a magnetic field, it actually does get attracted to it and it sticks to the magnet, which is a very cool experiment to do. So that's magnetism, and the last one is periodic trends. So I didn't want to draw out a whole periodic table, but orbitals sort of explain earlier ideas like valency a lot better. So here we have hydrogen, which is 1s1 configuration, so 1 valence electron. Helium is 1s2, lithium is 2s1, so again it's 1 valence electron, which is, so you sort of see patterns emerging where the number of electrons in each orbital configuration, for example, the hydrogen and lithium are sort of similar acting in how they react. And again, for when you're talking about sodium, so Na would be 1s2, 2s2, 2p2, 3s1. So you can see that the valence shell, the 3s, only has one electron in it, so it behaves very similar to lithium. When you get to carbon, you can sort of see carbon bonds to four things. It has four valence electrons in the 2s2, 2p2. So you can sort of see where some of these bonding patterns and some of this valency stuff comes from a quantum mechanical level, from a more mechanistic level. So just following on from that, a bit of a question: what is the electron configuration for argon? So drawing it out, argon, so we have a 1s, we have a 2s, and we have a 2p, and we have 3 boxes for the x, y, and z. And in argon, it has 2, 4, 6, 8, 10 electrons, and it fills all of these up. And you can see that's sort of the characteristic for a noble gas. It has filled up all the orbitals in that principal quantum number. So its highest principal quantum number is 2, all of them are filled, so it's sort of a very stable molecule, doesn't really want to react. Especially down the bottom, where of so with smaller noble gases, the energy gaps between principal quantum numbers are huge. So you're talking about but for things like xenon, you can actually get that bonding to the fluorine, which is very weird because it is a noble gas, but I think it's octahedral or something, because some of the higher quantum states are less energetically separated. So the energetic difference between a 1s and a 2s orbital is huge, while between a 5s and a 6s is quite small, and that's because you've got this type of separation. So this is your infinity, n equals infinity, and n equals 1. You can see that the energy levels are actually getting closer and closer, and that's why you get some noble gases, supposedly, that do actually bond to stuff. So in the next video we'll start talking about molecular orbital theory, which starts giving us more of an idea of how this is useful in explaining bonding, which is what this is all about.